This is Project 10 of Johns Hopkins Software Development for Real-Time Embedded Systems 605.715. So let's start with the requirements for Project 10. It is Quadcopter downloading IMU and GPS data from the Raspberry Pi to the host machine via Bluetooth, using the IMU connected to the Arduino and GPS connected to the Raspberry Pi, mounted on the quadcopter and hopefully flying. Capture Roll+Pitch+Yaw data on the Arduino, send over I2C to the Raspberry Pi, capture GPS, latitude, longitude, altitude data on the Raspberry Pi, and then send the Roll+Pitch+Yaw data and Lat+Lon altitude via Bluetooth from Raspberry Pi to the host and display in the host. So for this video, I will start with the hardware, showing you my hardware setup. We'll then take a look at the software that I developed to be able to implement the requirements. Then we will capture the data while my quadcopter is flying. I will then transmit that data via Bluetooth from the Raspberry Pi to my host machine, and I will display that data on my host. So let's start with the hardware setup. You can see the remote control right here for the quadcopter. Here is my quadcopter here. And let's start with the first requirement, which says the IMU connected to the Arduino. So here is the BNO055 Adafruit absolute orientation sensor up top. And you can see that there's some wires that are on the side here that connect the IMU sensor, which is attached to this breadboard, down to the Arduino, which is in this brown casing right here, brown protective casing down below right here. So next, GPS connected to the Raspberry Pi. So down here is the GPS dongle, and here's the cord for that, and you can see it is connected into the back of the Raspberry Pi. Raspberry Pi is inside this black case right here. So mounted on the quadcopter, all of that is mounted on the quadcopter here. Okay. And you can see here I have a battery pack. I'll show you this here, which is in between the Arduino and the Raspberry Pi. And this battery pack right here will plug in to the side right here. And this battery will power the Raspberry Pi. And in order to get power to the Arduino, I connected the Arduino and the Raspberry Pi for a USB cable. And what this does is this just provides, Raspberry Pi provides power to the Arduino via that blue cable right here. Okay, so we're going to capture the Roll+Pitch+Yaw data, which is being collected by this sensor, into the Arduino. That's going to travel down, these data is going to travel down these multicolored cables into the Arduino. And then the Arduino is going to send that data over I2C to the Raspberry Pi. So how that happens is, if you can see on the side here, I have some cables on this underneath the Arduino here, which are connected to the I2C pins in the Arduino. And those connect down into the Raspberry Pi underneath, which you can't see because it's nestled under here under the battery. But these white, orange, and green, these cables, I2C to Arduino, I2C to Raspberry Pi. So data goes sensor, Arduino, then travels down into the Raspberry Pi, I2C down here. And here's our battery pack on the side of the quadcopter, which powers the entire quadcopter up. So that is the hardware setup. And now let's take a look at the software setup that enables all of the data to be captured.
Let's take a look at the software now that helps fulfill the requirements. There were 3 programs that I developed. The first program is a Python script that logs the GPS latitude, longitude, and altitude data into a text file on the Raspberry Pi. Let's take a look at that one right now. Name of this program is GPS Polar. And we have some libraries up top here. The first real line of code, we open a new new text file called GPS_data. This is where I will log the GPS data, the latitude, longitude, and altitude data. The workhorse class below is called GPS Polar. This is what reads the GPS data from the GPS dongle. And then below, I have a while loop, which prints the latitude, longitude, and altitude data, and it does so every 5 seconds. So you see time.sleep 5. So that's every 5 seconds, we read the GPS data and we print it to our text file. So let's close that. The second program is also a Python script like the GPS program. And this second program is the code for the Raspberry Pi, which is responsible for requesting IMU data via I2C from the Arduino slave. The Raspberry Pi is the master and the Arduino is the I2C slave. And here's the Python script right here that runs on the Raspberry Pi. So when this runs, we are going to open a new file because we need to log the IMU data that we retrieve from the Arduino. So this W means write, open IMU, new text file, and then we're going to write to that file the roll, pitch, and yaw data. We need to set up an address. Here's the slave address, hex 4, and this is where enables the Raspberry Pi to identify the Arduino I2C address here. And here is the workhorse method. It's called request reading. And this method reads a block at the slave address, which is this hex 4 of 12 bytes, and it stores that data into a variable called reading. And then we need to extract that data, those 12 bytes, into something that we can actually print to our text file. So here, I'll go through the roll data right here. If the first byte of our 12 byte block, if that first byte is less than 1, that means that the roll data is positive. So the degree reading for the roll data is positive. Otherwise, it is negative. And so that first byte, the first byte is going to be the identifier to enable me to see is the roll negative or positive. And it's the same for the pitch and the yaw. So the first byte, which is going to be, in this case, it's reading 4, which is actually the 5th byte. If that's less than 1, if it's 0, that means that the pitch data is positive. Otherwise, it is negative. So that's my identifier. So the roll, pitch, and yaw data, they're all 3 digits, but I use that first digit to identify if it's positive or negative. So that's how this works here, these conditional statements. And then once I have extracted the roll, pitch, and yaw data from the byte readings, I then want to both print this data to the console, and I also want to write this data to the text file, which we opened up in the beginning of the program. And then when I'm done and I press keyboard interrupt, Control-C, or exit the system, I want that file to close. And here is our simple while loop, which is going to request IMU data via I2C from the Arduino, request reading every 5 seconds. So this time.sleep 5 means request this every 5 seconds. So that's our Raspberry Pi script. Just going to read I2C from the Arduino. Let's close this now and let's go to our last program. This last program is on Arduino, and this enables the Arduino to read the roll, pitch, and yaw data from the B&O 055 Adafruit sensor. So we have our wire library, Adafruit library. This helps to, wire library is I2C, helps to read the I2C protocol. And then we have the Adafruit sensor library right here. Going to scroll down and I'll point out some of the more important pieces of the code. Here's the slave address. Remember that hex 4 from the Raspberry Pi Python script. This declaration right here makes Arduino slave to the Raspberry Pi. Here is the byte array. I named this IMU data. It's going to store 12 bytes of data. So remember, we have the first 4 bytes are going to be the roll data. The second 4 bytes is going to be the pitch data. And then the last block of 4 bytes are going to be the yaw data. And the first byte, as I mentioned previously when I was going over the Python code for the Raspberry Pi reading I2C from the Arduino, this first byte will be either 0 or 1, depending on the sign of the roll data. Similarly, this 5th byte here is going to be the sign of the pitch data. And this byte here is going to be the sign of the yaw data. And the 3 digits after the sign byte are going to actually hold the digits, 3 digits, for the roll, pitch, and yaw data. Here are variable decorations here for the roll, pitch, and yaw. It's integers. I'm going to use this for the digit extraction. And the reason why I do digit extraction is because a byte, this byte right here, can only hold 0 to 255 for the numbers. So what I did is I read the roll, pitch, yaw data, and I just extract each digit. And I put each digit into the byte array. And so that's how I'm able to send that data I2C from the Arduino back to the Raspberry Pi. Here's our end program method. This method ends the program. I type in an exclamation point into the serial monitor, and this stops the reading here. Here's some methods that facilitate the sensor readings, calibration. Just keep going down. Here is the send IMU reading. This particular method executes when a request is received from the Raspberry Pi. So remember, we're requesting readings every 5 seconds from the Raspberry Pi. When the Raspberry Pi requests this data via I2C from the Arduino, Arduino is going to respond back by writing that IMU data byte array, and at the length of that, it's going to be 12 bytes, as I mentioned previously. Here is a helper method. This method right here reads an integer. In this case, it's going to be the roll, pitch, and yaw readings from the B&O 055 sensor, and it's going to extract a digit at a particular position, int in, a given position right here. And it's going to return a single byte, which is going to be the digit that it extracts from that integer. Here's the setup method. This runs upon startup of the Arduino automatically. Set the baud rate 9600, print some data to the serial monitor. Let's initialize the sensor below here. Here's some basic information for the sensor, some basic methods that get the sensor going, and some details on the sensor. We're going to set up the wire library, make Arduino the slave. That's this wire.begin slave address. And then these last 2 methods define the callbacks for I2C communication. This first one, this wire.onReceive, is used to specify a function when data is received from the Raspberry Pi master. And the second one is a real workhorse, which is going to specify the function, in this case, send IMU reading. It's going to call that send IMU reading each time the master Raspberry Pi requests data. And now we are in the loop of the Arduino, and here is where we actually take the readings. So yaw, pitch, in Roll, and we are going to store that data inside the yaw, pitch, and roll integers. And then below, I am going to extract the digits from those roll, pitch, and yaw integers. And I'm going to store each digit into the IMU data byte array, which will get sent over via I2C to the Raspberry Pi. And that's where this method that I mentioned before comes into play. I'm going to send that IMU data byte array over to the Raspberry Pi each time a request for a reading is made by the Raspberry Pi. So that is the software. And now we are going to close this software, and I'm going to fly the quadcopter, and we are going to run the programs and save the data to text files. So let's do that now. Okay, here I am. Just enter the command to start up the GPS data. You can see the text file here that was created by the Python script. And the latitude, longitude, and altitude data are now being read into that text file. Now let's open up the serial monitor. We are looking here at the roll, pitch, and yaw data being read by the Arduino from the BNO055 sensor. And now I'm going to type in the script, Python script, so that the Raspberry Pi can request those readings from the Arduino. And now you can see the roll, pitch, and yaw data being printed out to the terminal. And in the meantime, this data is also being recorded in the text file. Okay, I'm going to enter the Sentinel, exclamation point. We are done collecting roll, pitch, and yaw data. Stop the Python scripts, both the Raspberry Pi script and the GPS script, by pressing Control-C. And you can see here the two text files that were saved. GPS data have our latitude, longitude, and altitude data, which was written to this text file. And the IMU data, which showing the roll, pitch, and yaw data, which is written to this text file. And you can see the sign on each. Now we're going to send these files, the IMU data and GPS data, via Bluetooth to my host computer. Need to find the file on the Raspberry Pi. Under Documents, Python, here's the GPS data. Going to send this. I need to locate my laptop on the Bluetooth network. I can see here the name is laptop M175 on my host. So I'm going to go back to my Raspberry Pi. I'm going to select that option, click OK, and send the text file with the GPS data. Save it to my desktop on my host computer, click Finish. Now I need to send the IMU data, which has the roll, pitch, and yaw data. Again, I need to find that document and then my documents on my Raspberry Pi. Under Documents, Python, and let's just get ready on my host computer to be able to receive this file. So I'm going to click on Receive Files on my host computer. Going back to the Raspberry Pi, I'm going to select the IMU data text file, click OK, select my laptop on the Bluetooth network, click OK, and we are sending the files via Bluetooth from the Raspberry Pi to my host computer. File was sent, transferred successfully. I'm going to save this file to my desktop on my host computer. Click OK. And now both files, the IMU data and the GPS data, are on my host computer. Okay, I have my GPS data, IMU data. I'm going to open both of these files using Notepad++. You can see here the latitude, longitude, and altitude data from the GPS data file. This is being displayed on my host computer, an HP Omen with Windows 10. That's the GPS data. So we'll close that, and now let's open up the IMU data using Notepad++, and we can see the roll, pitch, and yaw data in nice, neat columns here displayed on my host computer. And that is it.